something that will fundamentally change how you understand death itself. We're going to discover what happens when gravity becomes so extreme, so overwhelmingly powerful, that it can stretch matter into impossibly thin strands across the fabric of space-time. We're going to learn about spaghettification, a process so violent and so absolute that it represents perhaps the most terrifying fate any object in our universe can experience. By the end of this journey, you're going to understand a phenomenon so bizarre that even the greatest minds in physics find it both fascinating and deeply unsettling. Before we begin, if you enjoy these deep explorations of the cosmos and the strange physics that governs our reality, a quick like or subscribe would really help the channel grow. Now let's begin our descent into the darkest corners of the universe. Space is not a friendly place. This is something we understand instinctively, even if we don't always appreciate the full scope of just how hostile the cosmos truly is. The vacuum itself would kill an unprotected human in roughly 90 seconds. Radiation from our own sun would cook us without the protective blanket of Earth's magnetosphere. The cold of deep space, hovering just a few degrees above absolute zero, would freeze biological tissue solid. These dangers are immediate and comprehensible, but there exists another threat in our universe, one so extreme and so alien to our everyday experience that it requires us to fundamentally reconsider what we think we know about matter, about space, and about the very nature of physical existence. Black holes are, without exaggeration, the most extreme objects that exist in our observable universe. They represent the ultimate victory of gravity over all other forces. They are places where the normal rules of physics break down, where time itself behaves in ways that defy our intuition, and where anything that ventures too close faces a fate worse than simple destruction. That fate has a name, and that name is spaghettification. The term might sound almost whimsical, even humorous. It was popularized by the legendary theoretical physicist Stephen Hawking in his 1988 best-selling book, A Brief History of Time. In that work, Hawking described a thought experiment involving a fictional astronaut who falls into a black hole. As this unfortunate traveler approaches the event horizon, Hawking explained, they would find themselves stretched like spaghetti by the immense gravitational forces at play. The term stuck, entering the lexicon of both professional astrophysicists and the general public. But make no mistake, despite its playful name, spaghettification represents one of the most violent processes in the known universe. To understand spaghettification, we first need to understand gravity in a way that goes beyond the simple concept of objects falling toward other objects. We need to understand what happens when gravity isn't uniform, when different parts of an object experience dramatically different gravitational pulls. We need to understand tidal forces. Here on Earth, we're familiar with tides. Twice each day, our oceans rise and fall in response to the gravitational influence of the moon, and, to a lesser extent, the sun. But have you ever stopped to consider why tides work the way they do? It's not simply that the moon pulls on our water. If the moon's gravity affected all parts of Earth equally, there would be no tidal effect at all. The entire planet would simply accelerate toward the moon as a single unit, and we'd notice nothing unusual about our oceans. The key insight is that the moon's gravity doesn't affect all parts of Earth equally. The side of Earth facing the moon is roughly 12,000 700 kilometers closer to the moon than the center of Earth, and the far side of Earth is the same distance farther away. Because gravitational force decreases with distance, the near side of Earth experiences a slightly stronger pull from the moon than the center, and the center experiences a slightly stronger pull than the far side. This difference in gravitational force across the diameter of Earth is what creates tides. The near side water bulges toward the moon because it's being pulled more strongly than the solid Earth beneath it. The far side water bulges away from the moon because the solid Earth is being pulled more strongly toward the moon than the water on the far side. This difference in gravitational force from one point to another is what physicists call a tidal force, or a gravitational gradient. On Earth, this gradient is subtle. The difference in the moon's gravitational pull between your head and your feet is so vanishingly small that you could never perceive it. According to calculations, the difference in gravitational force between the head and feet of a person standing on Earth's surface due to Earth's own gravity amounts to approximately 0.00007% of the total gravitational force experienced. This is why we don't feel ourselves being stretched as we go about our daily lives. But what happens when we approach a much more massive object? What happens when we get much, much closer to an intense gravitational source? The tidal forces increase dramatically. The mathematical relationship is precise and unforgiving. Tidal force is directly proportional to the mass of the gravitating body and inversely proportional to the cube of the distance from it. That cubic relationship is crucial. If you have your distance from a massive object, the tidal force you experience doesn't merely double or quadruple, it increases by a factor of 8. Get 10 times closer and the tidal force increases by a factor of 1,000. This is where black holes enter our story, and this is where things become truly terrifying. A black hole is what remains when a sufficiently massive star exhausts its nuclear fuel and collapses under its own gravity. During a star's life, the outward pressure from nuclear fusion in its core balances the inward pull of gravity. When the fuel runs out, there's nothing left to hold the star up. If the star is massive enough, typically more than about 20 times the mass of our sun, no known force can halt the collapse. The matter falls inward, crushing itself to incredible densities. The gravitational field becomes so intense that even light cannot escape. A black hole is born. The boundary around a black hole, from which nothing can escape, is called the event horizon. This is not a physical surface, not something you could touch or see. It's a mathematical boundary, a sphere in space marking the point of no return. Cross the event horizon, and your fate is sealed. You will fall toward the center. Nothing can save you. No amount of thrust from any conceivable engine, no rescue mission, no force in the universe. The event horizon is absolute. The size of the event horizon depends on the mass of the black hole. This relationship was first calculated by the German physicist Karl Schwarzschild in 1916, just months after Albert Einstein published his general theory of relativity. Schwarzschild solved Einstein's field equations for a non-rotating, spherically symmetric mass, and in doing so, he determined the radius at which the escape velocity equals the speed of light. This radius is now called the Schwarzschild radius in his honor. The equation is elegant in its simplicity. The Schwarzschild radius equals 2 times Newton's gravitational constant times the mass, divided by the speed of light squared. For a black hole with the mass of our Sun, this works out to approximately 3 kilometers. Think about that for a moment. All the mass of the Sun, roughly 2 nonillion kilograms, compressed into a sphere just 6 kilometers across. For comparison, the Sun's actual radius is about 700,000 kilometers. A stellar mass black hole, containing perhaps 10 times the mass of the Sun, would have a Schwarzschild radius of about 30 kilometers. The supermassive black hole, at the center of our Milky Way galaxy, Sagittarius A star, has a mass of approximately 4 million solar masses and a Schwarzschild radius of about 12 million kilometers, roughly 17 times the radius of our Sun. At the very center of a black hole, according to general relativity, lies the singularity. This is a point of theoretically infinite density, where all the black hole's mass is concentrated into a region of zero volume. The singularity represents the ultimate breakdown of our physical theories. General relativity predicts its existence, but cannot describe what happens there. Quantum mechanics, which governs the behavior of matter at the smallest scales, also fails to provide a complete picture. Physicists widely believe that a complete theory of quantum gravity, which we do not yet possess, would be needed to truly understand the nature of singularities. For now, the singularity remains one of the deepest mysteries in physics, but for our purposes tonight, the singularity is almost beside the point. Long before any object reaches the singularity of a black hole, it will be destroyed by spaghettification. Long before the exotic physics of infinite density becomes relevant, the brute force of tidal stretching will tear that object apart at the atomic level. Let's consider what would actually happen if a human being were to fall into a stellar mass black hole, one with perhaps 10 times the mass of our Sun. This is not merely an exercise in morbid curiosity. Understanding this process illuminates fundamental truths about gravity, about matter, and about the nature of extreme physics. Imagine you are an astronaut who has, through some catastrophic accident or perhaps deliberate choice, found yourself falling toward such a black hole. Perhaps you were part of a mission studying this cosmic phenomenon from what you believed was a safe distance. Perhaps your spacecraft suffered a catastrophic failure. The how doesn't matter. What matters is that you are now in free fall toward the black hole, and there is no turning back. At first, you might not notice anything unusual. You are in free fall, which means you are weightless, just as astronauts aboard the International Space Station are weightless. The black hole's gravity is immense, but at a sufficient distance, that gravity is nearly uniform across your body. Your head and your feet are experiencing almost the same gravitational pull. You're falling, accelerating, but the tidal forces are negligible. As you get closer, however, things begin to change. The tidal gradient steepens. Your feet, being closer to the black hole than your head, start to experience a noticeably stronger gravitational pull. You begin to feel a gentle stretching sensation, as though invisible hands are pulling at your ankles and your scalp in opposite directions. At the same time, the parts of your body on either side of you are being pulled slightly inward toward the center of mass of the black hole, causing a subtle compression from the sides. The mathematics tell us that for a stellar mass black hole of 10 solar masses, a human being would begin to experience uncomfortable tidal forces at a distance of roughly 700 kilometers from the center. This is far outside the event horizon, which for such a black hole would be at about 30 kilometers. The forces would become lethal, capable of tearing a human body apart at a distance of perhaps 100 to 200 kilometers, still well outside the event horizon. This is a crucial point. For stellar mass black holes, spaghettification occurs before you ever cross the event horizon. You would be killed, stretched into an impossibly thin strand of matter, while still technically outside the black hole. An observer watching from a safe distance, if they could somehow see through the intense gravitational lensing effects, would witness your demise before you reached the point of no return. The process of destruction would be rapid, but not instantaneous. As the tidal forces increase, your body would begin to stretch. Your spine would elongate as your feet are pulled faster than your head. Your limbs would be drawn out. Simultaneously, you would be compressed from the sides, squeezed toward a narrower and narrower width. The combination of vertical stretching and horizontal compression would reshape your body into an increasingly long, thin form. At some point, the tidal forces would exceed the tensile strength of your tissues. Muscles would tear, bones would fracture and then shatter. Blood vessels would rupture. Your body would come apart, not in an explosion, but in a stretching, a pulling apart into separate pieces. But the process wouldn't stop there. Each piece would itself continue to be stretched and compressed. The fragments would become smaller fragments. Those would become smaller still. The tidal gradient continues to steepen as the remains fall closer to the singularity. Eventually, the forces would become strong enough to overcome the electromagnetic bonds that hold molecules together. Based on what we understand about bond energies and the extreme forces involved, individual molecules would be torn apart into their component atoms. Then, as the remains approached even closer to the singularity, even atomic nuclei might be disrupted. Though at this point we are entering realms where our physics becomes increasingly uncertain and our predictions rely on extrapolation from known principles. The end result, according to current theoretical understanding, is a thin stream of subatomic particles spiraling into the singularity. What was once a human being, with all the incredible complexity of biological life, with thoughts and memories and hopes and fears, has been reduced to a ribbon of fundamental particles, stretching across space-time, feeding into the hungry maw of the black hole. The term spaghettification, despite its almost comical name, perfectly captures this image. Matter is stretched and thinned, pulled into long strands, like pasta being made by some cosmic chef with a particularly dark sense of humor. The process is violent, thorough, and absolutely final. But here is where the story takes an interesting turn. What we've described applies to stellar mass black holes, those formed from the collapse of massive stars. But not all black holes are the same size, and the size of a black hole fundamentally changes the nature of spaghettification. Supermassive black holes, the giants that lurk at the centers of galaxies, have masses ranging from hundreds of thousands to billions of times that of our Sun. Sagittarius A star, at the center of our Milky Way, weighs in at about 4 million solar masses. The black hole at the center of the galaxy Messier 87, famously imaged by the Event Horizon Telescope in 2019, has a mass of approximately 6.5 billion solar masses. The current record holder for the most massive known black hole, TON 618, has an estimated mass of 66 billion times that of our Sun. For these supermassive black holes, something counterintuitive happens. The event horizon is much larger, but the tidal forces at the event horizon are much weaker. This is because the tidal force depends not just on mass, but on how quickly gravity changes with distance. And for a larger black hole, the gravitational gradient at the event horizon is gentler. Consider the numbers. For a supermassive black hole of 1 million solar masses, the Schwarzschild radius is about 3 million kilometers. At this event horizon, the tidal force experienced by a human-sized object would be roughly equivalent to hanging a small apple about 80 grams from your feet. This is barely noticeable. You could cross the event horizon of such a black hole without experiencing any immediate discomfort from tidal forces. You wouldn't be spaghettified at the threshold. For an even larger supermassive black hole, say 1 billion solar masses, the event horizon is about 3 billion kilometers. The tidal force at this horizon would be negligible, far too small for a human to perceive. You could fall through the event horizon without feeling anything unusual at all, at least not from tidal stretching. This leads to a strange and unsettling possibility. An astronaut falling into a sufficiently large, supermassive black hole would cross the event horizon without any dramatic physical sensation. One moment you would be outside the black hole, in principle able to send signals back to the universe. The next moment you would be inside, forever cut off from the outside. But you wouldn't feel the transition. There would be no physical barrier, no sensation of crossing a threshold. The event horizon is not a wall. It's a point of no return that you might not even notice as you pass through it. But don't mistake this for safety. Once inside the event horizon, your fate is sealed. You are falling toward the singularity. And while the initial tidal forces might be gentle, they will grow stronger as you approach the center. Eventually, even inside the most massive, supermassive black hole, you will be spaghettified. The destruction is merely delayed, not avoided. Physicists have calculated that for a supermassive black hole, one of 1 million solar masses, a person crossing the event horizon might survive for several minutes, perhaps even hours, as they fall toward the singularity. The exact time depends on the specific trajectory and the rotational characteristics of the black hole. During this time, you would be inside a black hole, cut off from the universe, falling toward your inevitable doom, but still alive and conscious. You would have time to contemplate your situation, to observe the bizarre visual phenomena caused by the extreme gravitational lensing, to watch the universe outside become distorted and compressed into an ever-narrowing ring of light behind you. What would you see during this descent? This question has fascinated physicists and science fiction writers alike. General relativity tells us that light bends in strong gravitational fields. Near a black hole, this bending becomes extreme. Looking back the way you came, you would see the universe compressed into a bright ring, with the blackness of the black hole's interior filling more and more of your visual field. Looking forward toward the singularity, you would see essentially nothing, an absolute darkness from which no light emanates. As you fell deeper, time dilation would become increasingly significant. Time, according to general relativity, passes more slowly in stronger gravitational fields. To an outside observer, if one could somehow observe your descent, You would appear to slow down as you approached the event horizon. Your radio signals would become stretched to longer and longer wavelengths, redshifting toward invisibility. From the outside perspective, you would never quite reach the event horizon. You would appear to freeze in time at the threshold, fading and reddening until you became invisible. But from your own perspective, time would seem to pass normally. You would fall through the event horizon in finite time, continuing on toward the singularity. There would be no paradox here, merely the strange consequences of relativistic physics. Different observers experience time differently, and near a black hole, these differences become extreme. One of the most disturbing implications of this is the question of what you would see of the external universe as you fell. Based on how general relativity describes the relationship between gravity and time, this could imply that as you approached and crossed the event horizon, you would see future events in the external universe playing out at an accelerated rate. Light from the universe would be blue shifted as it fell in with you. If these mathematical models hold true in such extreme conditions, you might, in principle, see the future history of the cosmos compressed into your final moments. Some calculations suggest you might witness billions of years pass in the universe during your descent, though the extreme distortion would likely make any coherent observation essentially impossible. We should acknowledge the limits of our knowledge here. No one has ever fallen into a black hole and reported back. General relativity provides our best theoretical framework, but it may not capture the full reality, especially in the extreme conditions near the singularity where quantum effects likely become important. What actually happens to consciousness, to subjective experience in such extreme conditions, is a question that science cannot yet answer. What we can say with more confidence is what happens to matter itself, at least until the point where our physics breaks down. Spaghettification is real. The mathematics that predict it are well understood and have been tested in less extreme conditions. Tidal forces are not exotic physics. We experience them every day in the rise and fall of ocean tides. What makes black holes different is not the type of force involved, but the magnitude. Black holes are simply tidal forces taken to an extreme that destroys anything that ventures too close. And we have now observed this destruction directly, not of humans, of course, but of stars. On October 12, 2020, astronomers announced that they had witnessed, for the first time in detail, the spaghettification of a star by a supermassive black hole. The event, designated AT2019QIZ, occurred in a spiral galaxy in the constellation Eridanus, approximately 215 million light-years from Earth. This made it the closest tidal disruption event ever observed, allowing for unprecedented detail in the observations. The star at the center of this cosmic drama was similar in mass to our own Sun, approximately 1 solar mass. It had wandered too close to a supermassive black hole, weighing approximately 1 million times the mass of the Sun. As it approached, the tidal forces began to tear it apart. Using telescopes from the European Southern Observatory, including the Very Large Telescope and the New Technology Telescope in Chile, along with the Las Cumbres Observatory Global Telescope Network and NASA's Neil Gehrels Swift satellite, a team of astronomers led by Matt Nichol of the University of Birmingham observed the event over a 6-month period. They watched as the star was stretched into long strands of material, with approximately half of its mass being captured by the black hole, while the other half was ejected outward in a powerful blast of material traveling at speeds up to 10,000 kilometers per second. The observations revealed something important that had previously only been theorized. When a black hole devours a star, the process is messy. The spaghettified material doesn't simply fall quietly into the black hole. Instead, the energy released as stellar matter is consumed propels debris outward, creating a curtain of dust and gas that can obscure the view. This had made previous tidal disruption events difficult to study in detail, but because AT2019 QIZ was detected early, just a short time after the star was first ripped apart, astronomers could see the curtain being drawn up, so to speak, and could study the process from near its beginning. Kate Alexander, a NASA Einstein Fellow at Northwestern University, who was part of the research team, described this as a unique peek behind the curtain, providing the first opportunity to pinpoint the origin of the obscuring material and follow in real time how it engulfs the black hole. This observation was not merely of academic interest. Studying tidal disruption events helps astronomers understand supermassive black holes, which are notoriously difficult to observe directly because they emit no light of their own. They also provide insights into how matter behaves under extreme gravitational conditions, testing our theories of physics in regimes that cannot be replicated in any laboratory on Earth. The team described AT2019 QIZ as potentially serving as a Rosetta Stone for interpreting future observations of tidal disruption events, with new observatories coming online, including the European Southern Observatory's extremely large telescope. Astronomers expect to detect many more of these events, allowing for increasingly detailed studies of how black holes consume matter. Tidal disruption events like AT2019 QIZ are relatively rare. Astronomers estimate that they occur in a given galaxy roughly once every 10,000 to 100,000 years. However, because we can observe many galaxies, we detect roughly 1 to 2 dozen per year. With more sensitive instruments, that number is expected to increase dramatically. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to detect hundreds of tidal disruption events once it begins full operations. These events remind us that spaghettification is not merely a theoretical curiosity. It is happening right now, somewhere in the universe, as stars wander too close to the supermassive black holes that lurk at the centers of galaxies. Every few decades, in our own Milky Way, a star likely meets this fate at the hands of Sagittarius A star, the supermassive black hole at our galaxy's center. While relatively quiescent compared to some active galactic nuclei, still occasionally feeds on unfortunate stars that stray too close. The history of our understanding of these events stretches back several decades. The theoretical framework was laid in 1975, when Jack Hills first proposed that stars could be tidally disrupted by massive black holes. In 1988, the renowned astrophysicist Martin Rees described how approximately half of the disrupted stellar material would remain gravitationally bound to the black hole, eventually accreting onto it and forming a luminous disk. This accretion process, Rees predicted, would produce a distinctive flare of electromagnetic radiation that could reveal the presence of an otherwise dormant black hole. The first observational evidence for tidal disruption events came in the early 1990s using the Rosetta X-ray satellite during its all-sky survey. These early detections were tentative, but over the following decades, improving technology led to increasingly confident identifications. As of 2024, astronomers have observed roughly 100 confirmed tidal disruption events, with detections spanning optical, infrared, radio, and X-ray wavelengths. Some of these events have been particularly spectacular. Swift J1644+57 detected in 2011 involved a tidal disruption that launched a relativistic jet, a beam of particles accelerating to near the speed of light directly on toward Earth. The jet lasted approximately 1.5 years before shutting off. A SASSN-14LI, detected in 2014, provided the first radio detection of a non-relativistic outflow from a tidal disruption event. A T2018 HYZ exhibited an unusual delayed radio outflow, remaining quiet in radio frequencies for approximately 750 days after the initial event before brightening dramatically, suggesting complex physics in the aftermath of the stellar destruction. These observations have transformed tidal disruption events from theoretical predictions to powerful tools for probing black hole physics. They allow astronomers to estimate black hole masses, study accretion physics under extreme conditions, and potentially detect intermediate mass black holes, which have proven difficult to find through other means. Which brings us to an important question. How close is the nearest black hole to Earth? And should we be worried about spaghettification in our cosmic neighborhood? For most of human history, we couldn't answer this question with any certainty. Black holes, by their nature, emit no light. We could only detect them indirectly, through their gravitational effects on nearby matter, or through the radiation emitted by material falling into them. This meant that only active black holes, those currently accreting matter, could be observed. Dormant black holes, those sitting quietly with no nearby material to consume, remained invisible. This changed with the European Space Agency's Gaia spacecraft. Launched in 2013, Gaia has been mapping the positions and motions of billions of stars in our galaxy with unprecedented precision. By carefully measuring how stars move, astronomers can detect the gravitational influence of unseen companions, including black holes. In November 2022, astronomers announced the discovery of Gaia BH1, the closest known black hole to Earth. Located approximately 1,560 light-years away in the constellation Ophiuchus. Gaia BH1 has a mass of approximately 10 times that of our Sun. It exists in a binary system with a Sun-like companion star, which orbits the black hole at about the same distance that Earth orbits our Sun. This companion star is what gave away the black hole's presence. Its motion, tracked precisely by Gaia, revealed that it was orbiting an unseen massive object. To be clear, 1,560 light-years is still an immense distance. At the speed of the Parker Solar Probe, currently the fastest spacecraft ever built, it would take approximately 40 billion years to reach Gaia BH1, far longer than the age of the universe. Even at the speed of light, the trip would take 15.5 centuries. There is no scenario in which Gaia BH1 poses any threat to Earth. Since the discovery of Gaia BH1, astronomers have found two additional nearby black holes using the same technique. Gaia BH2, announced in 2023, lies approximately 3,800 light-years away in the constellation Centaurus, also with a mass of roughly 10 solar masses. Gaia BH3, announced in 2024, is located approximately 1,926 light-years away in the constellation Aquila. At approximately 33 times the mass of our Sun, Gaia BH3 is the most massive stellar black hole ever discovered in the Milky Way. These discoveries represent a new class of black holes, ones that are completely dormant and were previously invisible. They orbit their companion stars at much greater distances than the black holes in X-ray binary systems, which are close enough to their companions to actively strip and consume stellar material. The existence of these wide-orbit dormant black holes suggests that many more such objects likely populate our galaxy. Based on theoretical models of stellar evolution and death rates, some estimates suggest the Milky Way may contain as many as 100 million stellar mass black holes, the vast majority of which would be dormant and invisible to traditional observation methods. Beyond these stellar mass black holes, the nearest supermassive black hole is Sagittarius A star at the center of our Milky Way galaxy, approximately 26,000 light-years from Earth. With a mass of approximately 4 million solar masses, Sagittarius A star is a relatively modest, supermassive black hole compared to the monsters found in some other galaxies, but it is still immensely powerful. The stars orbiting closest to it travel at speeds of several percent of the speed of light, the fastest stellar motions ever observed. Sagittarius A star is currently in a quiescent state, not actively consuming large amounts of material. However, observations suggest it does occasionally flare when gas or debris falls into it. If a star were to wander too close and undergo tidal disruption, the resulting flare would be visible across the electromagnetic spectrum, though the dust and gas between us and the galactic center would obscure much of the optical light. The key point to emphasize is that despite having perhaps 100 million black holes in our galaxy, Earth is in no danger from any of them. The nearest black hole is more than 1,000 light-years away. Gravitational effects at such distances are utterly negligible. Even Sagittarius A star, despite its 4 million solar masses, exerts less gravitational influence on Earth than a single person standing next to you. Gravity weakens with distance, and at 26,000 light-years, even a supermassive black hole is gravitationally irrelevant to our daily lives. The only way spaghettification could ever affect Earth would be if a black hole somehow entered our solar system, and the odds of this happening are essentially zero. Black holes don't roam the galaxy looking for things to consume. They follow ordinary gravitational orbits around the galactic center, just like stars do. The Milky Way is mostly empty space, and the chances of any black hole passing close enough to our solar system to pose a danger are vanishingly small over the entire lifespan of our Sun. This should be reassuring as you contemplate the nature of spaghettification. It is a real phenomenon, one that is happening to stars throughout the universe right now. But it is also a phenomenon that requires close proximity to a black hole, and we are fortunate enough to live in a relatively sparse region of the galaxy, far from any known gravitational threats. Now that we understand the basic physics of spaghettification and have seen evidence of it occurring on cosmic scales. Let's delve deeper into the details of what this process actually involves. Let's consider not just the broad strokes, but the specific physical phenomena that would occur as matter is stretched and compressed by tidal forces. The key to understanding spaghettification at a deep level is recognizing that it involves two simultaneous effects. The first is radial stretching, the pulling apart of matter along the direction toward the black hole. The second is tangential compression, the squeezing of matter perpendicular to that direction. Both effects arise from the same underlying cause, the gravitational gradient. Consider a person falling feet first toward a black hole. The feet, being closer to the black hole, experience a stronger gravitational pull than the head. This differential force acts to stretch the body along its length. At the same time, the gravitational field is directed toward the center of the black hole from all points around it. This means that the left side of the body is being pulled slightly toward the right, toward the center, and the right side is being pulled slightly toward the left. This differential direction of the gravitational force acts to compress the body from the sides. The mathematics of these forces can be worked out using Newtonian physics for a first approximation, though a complete treatment requires general relativity, especially close to the event horizon. For objects at a distance r from a mass m, the radial tidal acceleration across an object of length delta r is approximately 2 gm times delta r divided by r cubed. The tangential tidal compression is approximately half this value. These equations tell us that the tidal forces grow extremely rapidly as distance decreases. That cube in the denominator is crucial. As you fall closer to a black hole, the tidal forces don't just increase, they increase explosively. To put some concrete numbers to this, a person standing on the surface of Earth experiences a radial tidal acceleration between their head and feet of approximately 3 times 10 to the minus 6 meters per second squared. This is utterly imperceptible. A person at a distance of 100 kilometers from a 10 solar mass black hole would experience a radial tidal acceleration of approximately 10,000 meters per second squared, or roughly 1,000 times Earth's surface gravity. At a distance of 50 kilometers, this would increase to roughly 8,000 times Earth's surface gravity. At the event horizon, about 30 kilometers from the center, the tidal acceleration would exceed 10,000 times Earth's gravity, more than enough to tear a human body apart. Studies of human physiology suggest that the force required to pull apart the human body is approximately 9,000 newtons, or about 2,000 pounds of force. Historical records, including military manuals from the 19th century that documented the mechanics of execution by hanging, provide some data on this topic. They noted that too little force would fail to break the neck, while too much would cause decapitation. While these are approximate figures and would vary significantly between individuals, they give us a rough threshold for the forces that human tissue can withstand. Using this threshold, physicists have calculated that a human falling toward a stellar mass black hole of 10 solar masses would likely be killed by tidal forces at a distance of roughly 400 to 700 kilometers from the center, depending on the individual's size and orientation. This is more than 10 times the Schwarzschild radius of such a black hole, meaning death would occur well outside the event horizon. For supermassive black holes, the calculation yields very different results. For a black hole of 1 million solar masses, the distance at which tidal forces would become lethal is only about 200,000 kilometers from the singularity, which is well inside the event horizon at 3 million kilometers. For a black hole of 1 billion solar masses, the lethal distance shrinks to about 200 kilometers from the singularity, utterly negligible compared to the event horizon at 3 billion kilometers. This is why the size of the black hole matters so much for the experience of falling in. Stellar mass black holes would spaghettify you before you ever reached the event horizon. Supermassive black holes would allow you to cross the event horizon intact, extending your conscious experience of the fall, but ultimately delivering the same fate once you approached close enough to the singularity. Let's consider what happens at the material level as spaghettification proceeds. The human body is a complex structure held together by various forces. At the macroscopic level, we have tissues composed of cells, held together by cell junctions and extracellular matrix. Cells are held together by protein bonds and lipid membranes. Molecules are held together by covalent and ionic bonds between atoms. Atoms themselves are held together by the electromagnetic force, binding electrons to nuclei. Nuclei are held together by the strong nuclear force, binding protons and neutrons. Each of these binding forces has a characteristic strength, and each would be overcome at a different stage of the spaghettification process as the tidal forces increased. First to fail would be the macroscopic structures. Connective tissues would tear, blood vessels would rupture, bones would fracture, the body would come apart into progressively smaller pieces, each piece continuing to be stretched and compressed by the tidal forces. Next, the cellular structures would be disrupted. Cell membranes would be torn, releasing their contents. Proteins would be denatured as mechanical forces exceeded the strength of their folded structures. The chemical machinery of life would be destroyed. At higher tidal forces, individual molecules would be torn apart. The covalent bonds holding atoms together in molecules require significant energy to break, but the forces near a black hole singularity are more than sufficient. Molecules would be stripped down to their component atoms. Whether atomic nuclei themselves would be disrupted is less clear. The strong nuclear force that holds protons and neutrons together in the nucleus is extraordinarily powerful, billions of times stronger than the electromagnetic force that holds molecules together. Overcoming this force would require tidal accelerations far beyond anything found at the event horizons of known black holes. However, near the singularity itself, where densities and forces theoretically become infinite, even nuclear matter might be disrupted. At this point, we are in territory where our physics is genuinely uncertain. Some physicists have explored what might happen to matter approaching a singularity. One possibility, developed in work by Soviet physicists Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz in the late 1960s, is that the space-time near the singularity becomes chaotically oscillating. Their calculations suggested that matter falling toward the singularity would experience rapidly changing tidal forces, with the direction of stretching and compression rotating chaotically. They called this behavior mix-master dynamics, after a popular brand of electric mixer, because the effect on matter would be similar to what a mixer does to dough. Whether the mixed-master model accurately represents physical reality remains an open question. Current thinking suggests that quantum gravity effects, which we don't yet fully understand, would likely modify the behavior of spacetime near singularities. Some theoretical physicists have proposed that singularities might not actually exist in a complete theory of quantum gravity, that quantum effects could smear them out into finite density regions. Others have suggested that the interior of a black hole might connect to other regions of spacetime, functioning as a kind of wormhole. These remain theoretical possibilities rather than established facts, and with current technology, we have no way to test them directly. What we can say with confidence is that matter entering a black hole undergoes extreme violence. Whether that matter ends up as a classical singularity, as some kind of quantum fuzz, or as something else entirely, it first passes through a regime of intense tidal stretching that destroys any organized structure. Spaghettification is the last knowable stage before physics breaks down entirely. This brings us to one of the most mind-bending aspects of black hole physics, the question of what happens to information. In the 1970s, Stephen Hawking, building on earlier work by Jacob Bekenstein, made a startling prediction. Black holes are not truly black. They emit a faint glow of radiation, now called Hawking radiation, caused by quantum effects near the event horizon. This radiation is extremely weak for large black holes, with a temperature inversely proportional to the black hole's mass. A stellar mass black hole would have a temperature of only about 60 nanokelvin, far colder than any environment we could create in a laboratory. A supermassive black hole would be even colder. But weak as it is, Hawking radiation carries energy. Over immense timescales, this radiation would cause a black hole to slowly evaporate, losing mass until, eventually, after perhaps 10 to the 67th years, for a stellar mass black hole, it would disappear entirely. This timescale is unimaginably longer than the current age of the universe, which is only about 1.4 times 10 to the 10th years, but it is finite. This led to what became known as the black hole information paradox. In quantum mechanics, information cannot be destroyed. The fundamental equations of physics are reversible. Given complete knowledge of a system's state at any time, you can, in principle, calculate what its state was at any earlier time. But if a black hole evaporates completely into seemingly random thermal radiation, what happens to all the information about what fell into it? The detailed quantum state of every atom of every object that ever crossed the event horizon seems to be lost. This would violate one of the deepest principles of quantum physics. The resolution of this paradox remains one of the great unsolved problems in theoretical physics. Various proposals have been made, including the idea that the information is somehow encoded in subtle correlations in the Hawking radiation, that it is stored in some kind of remnant left behind when the black hole evaporates, or that it escapes through some as yet unknown mechanism. In 2004, Hawking himself conceded a famous bet with John Preskill, acknowledging that information probably is preserved, though he was not able to fully explain how. Most physicists today lean toward the view that information is preserved, but the precise mechanism remains elusive. What does this mean for spaghettified matter? If the current consensus holds true, the information that described you, every detail of your physical structure down to the quantum level, is not destroyed when you fall into a black hole. It would be scrambled beyond any practical possibility of recovery, encoded in the incredibly complex quantum state of the black hole or in the Hawking radiation that would eventually emerge over unimaginable timescales. But it would not, according to most current thinking, be truly lost. This is cold comfort, of course. The you that would emerge if you could somehow decode the information from Hawking radiation billions upon billions of years later would not be a conscious entity. It would be a quantum state that, in principle, could be connected back to your original quantum state through the reversible laws of physics. But the practical destruction of everything that made you who you are would be absolute and immediate as you underwent spaghettification. There is a certain philosophical poignancy to this. The laws of physics may preserve information in some abstract sense, but they do not preserve persons. Spaghettification is still death, absolute and final, regardless of what happens to the quantum information that once described your body. Let us now consider the different types of black holes that exist in our universe and how their varying properties affect the experience of spaghettification. Astronomers generally categorize black holes into 4 classes based on their mass. Stellar mass black holes, the most common type we have directly detected, have masses ranging from approximately 3 to about 100 times the mass of our Sun. These are formed from the gravitational collapse of massive stars at the end of their lives. When a star more than about 20 times the mass of our Sun exhausts its nuclear fuel, the core collapses. If the core remnant is more than about 2 to 3 solar masses, it will overcome even neutron degeneracy pressure, the quantum mechanical force that supports neutron stars, and collapse into a black hole. As of 2024, astronomers have detected approximately 50 stellar mass black holes in binary systems in our galaxy, with masses confirmed through gravitational observations. The LIGO and Virgo gravitational wave detectors have observed many more through the mergers of stellar mass black holes, with masses ranging up to about 90 solar masses in some cases. The largest stellar mass black hole found in the Milky Way is Gaia BH3 at approximately 33 solar masses. For these stellar mass black holes, spaghettification occurs outside the event horizon, as we discussed earlier. The relatively small size means steep gravitational gradients and lethal tidal forces well before you would cross the point of no return. At the other end of the scale are supermassive black holes, with masses ranging from hundreds of thousands to billions of times the mass of our Sun. These giants are found at the centers of most, if not all, large galaxies. The supermassive black hole at the center of our Milky Way, Sagittarius A star, has a mass of approximately 4 million solar masses. The black hole at the center of M87, the first to be directly imaged, has a mass of approximately 6.5 billion solar masses. The largest known supermassive black hole, TON618, has an estimated mass of approximately 66 billion solar masses. The formation of supermassive black holes remains an active area of research, and no single explanation has achieved consensus. They are too massive to have formed from the collapse of single stars, which suggests they must have grown through other mechanisms. Leading theories propose they may have grown from smaller seed black holes through accretion of gas and mergers with other black holes over billions of years. Some models suggest that massive seed black holes could have formed directly from the collapse of enormous gas clouds in the early universe without passing through a stellar phase. Recent observations from the James Webb Space Telescope have found surprisingly massive black holes in the early universe, which could imply that our current models of black hole growth need revision, or that some mechanism allowed for more rapid early growth than previously thought. For supermassive black holes, spaghettification occurs deep, inside the event horizon, after you have already crossed the point of no return. The journey from event horizon to destruction could take minutes or even hours of subjective time, depending on the size of the black hole and your trajectory. Between these two extremes is a class of objects called intermediate mass black holes, with masses ranging from roughly 100 to 100,000 solar masses. These are the rarest and most mysterious class of black holes. For many years, their existence was doubted. They are too massive to form from ordinary stellar collapse, but too small to be the supermassive monsters at galactic centers. Where would they come from? Current evidence suggests that intermediate mass black holes do exist, though they are difficult to find. The first direct evidence came in September 2020, when the LIGO-Virgo-Cagra collaboration detected a gravitational wave event designated GW190521, resulting from the merger of two black holes with masses of approximately 85 and 65 solar masses. The resulting black hole had a mass of approximately 142 solar masses, placing it firmly in the intermediate mass range. Other candidates have been found through various observational techniques. Some ultraluminous X-ray sources in nearby galaxies are suspected to harbor intermediate mass black holes. Some globular clusters may contain them at their centers. In 2021, astronomers reported evidence for an intermediate mass black hole of approximately 100,000 solar masses in a globular cluster in the Andromeda Galaxy. The formation of intermediate mass black holes is not fully understood, and several competing theories exist. They may form from the runaway merger of massive stars in dense stellar environments, from the collapse of massive gas clouds, or from the gradual accumulation of stellar mass black holes in dense star clusters. Each of these pathways has theoretical support, and it's possible that different intermediate mass black holes form through different mechanisms. For intermediate mass black holes, the experience of spaghettification would fall somewhere between the stellar and supermassive cases. A black hole at the lower end of this range, say a few hundred solar masses, would spaghettify you outside or near the event horizon. A black hole at the upper end, tens of thousands of solar masses, might allow you to cross the event horizon before tidal forces became lethal, though the margin would be much smaller than for true supermassive black holes. Finally, there is a hypothetical fourth class, primordial black holes. These are black holes that, according to some theoretical models, may have formed in the extreme conditions of the very early universe within the first second after the Big Bang. During this epoch, density fluctuations in the primordial plasma could theoretically have caused regions to collapse directly into black holes without passing through. Stellar formation. Primordial black holes, if they exist, could have a much wider range of masses than black holes formed from stellar collapse. Based on theoretical calculations, they could be as small as the mass of an asteroid, or as large as thousands of solar masses. The smallest primordial black holes, if they ever existed, would have evaporated through Hawking radiation long ago, as smaller black holes evaporate faster. But primordial black holes, larger than about 1 billion kilograms, could still exist today. No primordial black hole has ever been directly detected, and their existence remains unconfirmed. However, they remain theoretically possible and are one candidate explanation for dark matter, the mysterious substance that makes up approximately 27% of the universe's mass energy content. If dark matter consists of primordial black holes, they would have to be in a specific mass range to avoid detection by current observational constraints, and ongoing searches continue to narrow down the possibilities. The experience of spaghettification near a primordial black hole would depend entirely on its mass. A very small primordial black hole, if such objects exist, would have such a tiny event horizon that macroscopic objects could not fall into it intact. The spaghettification would begin at the atomic or molecular scale, as even individual atoms would be too large to fit through the event horizon without experiencing extreme tidal forces. This brings us to an interesting thought experiment. What is the smallest black hole that a human could fit through without being spaghettified at the event horizon? The answer turns out to be surprisingly large. A human body is roughly 2 meters tall. For tidal forces at the event horizon to be less than those experienced standing on Earth's surface, the black hole would need to have a mass of at least about 100,000 solar masses. This places it at the upper end of the intermediate mass range, or the lower end of the supermassive range. Any black hole smaller than this would spaghettify a human before they could reach the event horizon. This calculation assumes you want to be comfortable as you cross. If you merely want to survive the crossing, tolerating perhaps 100 times Earth's gravity in tidal stretching, you could manage with a somewhat smaller black hole, perhaps tens of thousands of solar masses. But anything less than that, and spaghettification would claim you before you ever reached the event horizon. Let's step back and consider what spaghettification tells us about the nature of the universe. In many ways, it is a reminder of the extreme indifference of physical law. The tidal forces that stretch matter near a black hole are simply gravity operating as it always does, following the same equations that keep your feet on the ground and the moon in its orbit. There is nothing malicious about a black hole, no intent to destroy. It is simply an extreme manifestation of a fundamental force. And yet the consequences for any complex structure that encounters these forces are devastating. The ordered arrangements of atoms that make up living beings, the molecular machinery that sustains life, the information encoded in DNA, the neural patterns that give rise to consciousness, all of this is erased by the simple mathematics of gravitational gradients. The universe, through its ordinary operations, is capable of destruction so complete that it reduces any organized structure to a thin stream of subatomic particles. This is not unique to black holes. Stars destroy matter in their cores through nuclear fusion. Neutron stars, with their intense gravity and magnetic fields, can disrupt matter in extreme ways. Cosmic rays can damage molecules. The universe is not a gentle place for complexity. What makes black holes special is the finality. Matter that falls into a star can eventually be recycled, ejected in stellar winds, or supernovae to form new stars and planets. Matter that is damaged can sometimes be repaired, but matter that crosses the event horizon of a black hole is gone from our universe forever, sealed behind a one-way boundary that no information can cross. This permanence is what makes black holes both fascinating and terrifying. They are cosmic endpoints, final destinations for matter and energy. The second law of thermodynamics tells us that entropy, disorder, tends to increase over time. Black holes represent perhaps the ultimate entropic endpoint, maximum disorder concentrated behind an impenetrable barrier. And yet black holes are not merely destroyers. They play crucial roles in the structure and evolution of the universe. Supermassive black holes at the centers of galaxies help regulate star formation, their energetic outbursts preventing galaxies from converting all their gas into stars too quickly. Black hole mergers, producing gravitational waves, provide a new window for observing the universe. The extreme conditions near black holes test our theories of physics in ways that no laboratory can match. Spaghettification, for all its horror, is a phenomenon that teaches us about the nature of gravity, about the limits of physical structure, and about the extremes that exist in our universe. In studying it, we learn not just about death, but about the fundamental laws that govern all matter and energy. As we approach the end of our journey tonight, let us reflect on what we have learned. Spaghettification is the name given to the stretching and compression of matter by extreme tidal forces, particularly those found near black holes. The term was coined by Stephen Hawking in his 1988 book, A Brief History of Time, and has since become standard terminology in astrophysics. The physics of spaghettification is not exotic. It is simply tidal force, the same phenomenon that creates ocean tides on Earth taken to an extreme degree. Tidal force results from the difference in gravitational pull across an extended object. Near a black hole, this difference becomes so large that it can overcome any binding force that holds matter together. The experience of spaghettification depends critically on the mass of the black hole. For stellar mass black holes, with masses up to about 100 solar masses, spaghettification occurs outside the event horizon. An infalling object would be stretched and torn apart before reaching the point of no return. For supermassive black holes, with masses of millions or billions of solar masses, spaghettification occurs deep inside the event horizon. An infalling object could cross the event horizon without experiencing harmful tidal forces, only to be destroyed later as it approached the singularity. We have observed spaghettification directly in the form of tidal disruption events, where stars are torn apart by supermassive black holes. The best studied example, AT2019QIZ, was observed in 2020 using telescopes from the European Southern Observatory and other institutions. These observations confirmed theoretical predictions and provided new insights into how black holes consume stellar material. The nearest known black hole to Earth is Gaia BH1, approximately 1,560 light-years away. This dormant stellar mass black hole poses no threat to Earth. Even the supermassive black hole at the center of our galaxy, Sagittarius A star, at 26,000 light-years distance, has negligible gravitational influence on our solar system. Spaghettification represents one of the most violent processes in the known universe. It reduces any complex structure to a thin stream of particles, destroying all organized information in the process. Whether this information is truly lost or merely scrambled remains an open question in physics, one connected to deep puzzles about quantum mechanics and gravity. And yet, for all its violence, spaghettification is simply physics, operating as it should. Gravity pulls, matter stretches. The universe continues, indifferent to the fate of any particular arrangement of atoms. In contemplating this process, we confront both the extremes that exist in our cosmos and the remarkable fact that we, from the safety of our small planet, can understand them. The next time you look up at the night sky, consider that scattered among those points of light are black holes, remnants of dead stars, lurking invisible in the darkness. Consider that at the center of our galaxy, 4 million solar masses of matter is compressed into a region smaller than Mercury's orbit, patiently waiting for the next star to wander too close. Consider that the same gravity that keeps your feet on the ground, that holds the moon in its orbit and shapes the tides, can become strong enough to stretch matter into impossible thinness. This is the universe we inhabit. It is a place of beauty and terror, of gentle stars and deadly voids, of life-giving warmth and absolute destruction. Spaghettification is just one thread in this vast cosmic fabric, but it is a thread that reveals much about the nature of physical law and the extremes that exist beyond our everyday experience. Thank you for joining me on this journey into the darkest corners of space. If you found this exploration illuminating, please consider liking and subscribing to the channel. Your support helps bring these deep dives into the cosmos to more curious minds. Until next time, sleep well, knowing that the nearest black hole is over 1,000 light years away, and that for now, at least, you are safe from the ultimate stretching of spaghettification. But before we part ways tonight, let us venture deeper still into some aspects of this phenomenon that deserve further exploration. For the curious mind seeks not just understanding, but thorough understanding. And spaghettification, in all its terrifying glory, has much more to teach us about the nature of our universe. Let us consider, in greater detail, the visual experience of approaching a black hole. We touched on this earlier, but the physics of light near these extreme objects is so strange, so fundamentally different from our everyday experience, that it warrants deeper examination. Light, as Einstein taught us, is not merely affected by gravity. It follows the curvature of space-time itself. Near a black hole, where space-time is dramatically warped, light traces out paths that would seem impossible in flat space. A photon that would normally travel in a straight line is forced to curve around the black hole, following the contours of distorted space-time. This effect creates a phenomenon called gravitational lensing. If you were approaching a black hole, you would see the stars behind it distorted, their images stretched and multiplied into rings and arcs around the dark center. As you got closer, this distortion would become more extreme. Stars that should be hidden behind the black hole would become visible, their light bent around the event horizon. Multiple images of the same star could appear at different positions in your field of view. At a certain distance, called the photon sphere, light can actually orbit the black hole. For a non-rotating Schwarzschild black hole, this occurs at 1.5 times the Schwarzschild radius. Photons at this distance, if given the precise initial direction, would circle the black hole indefinitely. This is an unstable orbit, however. Any slight perturbation would send the photon either spiraling into the black hole or escaping to infinity. If you could somehow hover at the photon sphere and look straight ahead, you would see the back of your own head. Light from behind you would loop around the black hole and return to your eyes. Of course, you could not actually hover at the photon sphere. The gravitational forces would be immense, requiring impossible acceleration to resist. And even if you could, you would be well within the region where spaghettification poses a serious threat for stellar mass black holes. As you cross the event horizon, the visual experience would become even more strange, according to our best theoretical models. General relativity tells us that once inside, all paths lead inward. Even light emitted outward would eventually curve back and fall toward the singularity. Based on these principles, the universe outside would appear compressed into an ever-shrinking bright ring behind you, as light from increasingly wide angles would need to bend more and more sharply to reach your eyes before you fell further in. Some calculations suggest that the compression of the external universe into this ring would cause it to appear blue-shifted, with light from distant stars appearing at shorter wavelengths. If these mathematical models accurately describe what would happen, time in the external universe would appear to pass more quickly from your perspective, though the extreme distortion would likely make coherent observation essentially impossible. How much of the universe's future you could theoretically observe depends on the size of the black hole and your exact trajectory, but estimates range from thousands to billions of years, all compressed into your final moments of consciousness. These are theoretical predictions based on general relativity, and we should acknowledge the limits of our certainty here. No one has ever fallen into a black hole and reported back on the experience. Computer simulations can model what physics predicts, but whether those predictions capture all relevant phenomena is unknown. Quantum effects, which become increasingly important at very small scales, might modify the experience in ways we cannot currently predict. What we can say is that the visual experience would be profoundly alien. Our brains evolved to interpret light in a flat space-time, where photons travel in straight lines at a constant speed. Near a black hole, these assumptions fail completely. Whether a human consciousness could make any sense of the input it received under such conditions is an open question. The brain might simply be overwhelmed, unable to construct a coherent visual picture from such distorted information. Let us also consider in more detail the role of rotation in black hole physics. So far, we have primarily discussed non-rotating Schwarzschild black holes, the simplest mathematical model. But in reality, essentially all black holes are expected to rotate, some quite rapidly. When a massive star collapses to form a black hole, it carries angular momentum with it. Just as an ice skater spins faster when they pull in their arms, the collapsing matter speeds up as it falls inward. The resulting black hole inherits this rotation, spinning at rates that can approach significant fractions of the speed of light at their event horizons. Rotating black holes are described by a different mathematical solution to Einstein's equations, called the Kerr metric, discovered by New Zealand mathematician Roy Kerr in 1963. Kerr black holes have several features that Schwarzschild black holes lack. Most notably, a rotating black hole has an ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Within the ergosphere it is impossible to remain stationary. Even if you fired rocket engines at maximum thrust directly against the direction of rotation, you would still be dragged around the black hole. The ergosphere is not a point of no return for matter. You can escape from it, but it is a region of inescapable rotation. The shape of a rotating black hole is also different. The event horizon is no longer a perfect sphere, but is slightly flattened at the poles and bulging at the equator. The singularity, rather than being a point, is theorized to be a ring lying in the equatorial plane of the black hole. How does rotation affect spaghettification? The answer is complex and depends on the direction of approach. If you fall in along the equatorial plane, the tidal forces are somewhat reduced compared to a non-rotating black hole of the same mass, because the event horizon is farther from the singularity in the equatorial direction. If you fall in along the polar axis, the forces are somewhat enhanced. The overall effect is modest for most realistic black holes, not changing the fundamental nature of spaghettification, but altering the details of where and when it occurs. There is one intriguing theoretical possibility associated with rotating black holes. According to the mathematics of the Kerr solution, the ring singularity is not a solid barrier. In principle, there are trajectories that pass through the center of the ring without hitting the singularity. Some mathematical models suggest these trajectories could lead to other regions of space-time, perhaps to other universes, or to distant regions of our own universe. This remains purely mathematical conjecture, however. This is the origin of the popular science fiction concept of black holes as portals or wormholes. However, most physicists working in the field are skeptical that this represents physical reality. The inner structure of Kerr black holes appears to be unstable to perturbations. Based on what we understand about these dynamics, any matter falling in would likely destabilize the interior structure, preventing passage through the ring. Additionally, to reach the ring singularity, you would need to pass through a region of effectively infinite tidal forces, which would spaghettify any physical object regardless of the geometric possibility of passage. These theoretical possibilities remain fascinating puzzles for physicists, but based on current understanding, they do not offer any practical escape from the fate of spaghettification. Whatever the ultimate structure of black hole interiors might be, the tidal forces encountered on the way in are more than sufficient to destroy any known form of matter. Let us now consider spaghettification in a different context. Neutron stars. While black holes represent the most extreme manifestation of gravitational tidal forces, neutron stars are not far behind. These incredibly dense stellar remnants, formed when stars between about 8 and 20 times the mass of the Sun explode as supernovae, pack masses comparable to the Sun into spheres only about 20 kilometers across. The gravity at the surface of a neutron star is approximately 200 billion times that at Earth's surface. If you could stand on a neutron star, which is impossible for many reasons, you would be crushed to a thickness of a few atoms by your own weight. An object dropped from a height of 1 meter would hit the surface at approximately 1,400 kilometers per second, or about 0.5% of the speed of light. Tidal forces on neutron stars are also extreme, though not quite as severe as near black holes. Calculations suggest that an object falling toward a neutron star would experience significant spaghettification as it approached the surface. The exact point at which tidal forces would become lethal for a human depends on the specific mass and radius of the neutron star, but it would typically be hundreds of kilometers from the surface, far enough away that you would be torn apart before you ever reached the star itself. The surface of a neutron star is a remarkable place if you could somehow survive to observe it. The matter is compressed to such densities that atomic nuclei are pushed together, forming what physicists believe to be a crystalline lattice of neutron-rich nuclei embedded in a sea of electrons and free neutrons. Deeper inside, the matter transitions to pure neutron fluid. Some theoretical models suggest that exotic phases like quark matter or strange matter could exist at the very center, though this remains an open question in nuclear physics. Physicists describe the expected structure of the interior as nuclear pasta, with regions of different density forming shapes reminiscent of spaghetti, lasagna, and other Italian dishes. The terminology is a playful nod to the spaghettification that would await any visitor. When neutron stars exist in binary systems with ordinary stars, they can gradually strip matter from their companions. This matter, spiraling inward, forms an accretion disk around the neutron star and eventually falls onto its surface. The impact of this material releases tremendous energy, causing X-ray bursts visible across thousands of light years. These systems, called X-ray binaries, were among the first evidence for the existence of neutron stars. If a neutron star has an initial mass close to the upper limit for neutron star stability, around 2 to 2.5 solar masses, depending on the precise equation of state, the accretion of additional matter can push it over the edge. The neutron star collapses further, becoming a black hole. In an instant, the solid surface disappears behind an event horizon, and any material that was on its way down experiences the full force of black hole spaghettification rather than the merely extreme conditions of neutron star approach. Binary neutron star mergers, where two neutron stars in close orbit spiral together and collide, are another context where extreme tidal forces play a crucial role. As the neutron stars approach each other, their mutual tidal forces begin to deform them from spherical shapes. In the final moments before merger, each neutron star is stretched toward its companion, distorted into elongated shapes by the intense gravitational gradient. The merger itself is among the most violent events in the universe. Two objects, each with the mass of the sun compressed into a volume smaller than a city, collide at significant fractions of the speed of light. The impact produces gravitational waves so powerful that they were detected on Earth by the LIGO and Virgo observatories. In August 2017, from a distance of approximately 130 million light-years. The event, designated GW 170817, was a watershed moment in astronomy. The first observation of gravitational waves from a neutron star merger, and the first time such an event was also observed electromagnetically. The tidal disruption of the neutron stars during the final moments of GW 170817 produced observable effects in the gravitational wave signal. By analyzing how the signal deviated from what would be expected for point masses, physicists could constrain the equation of state of neutron star matter, learning about the properties of matter at densities impossible to achieve in any laboratory. The merger also produced a kilonova, an explosion powered by the radioactive decay of heavy elements forged in the collision. The intense neutron flux during the merger allows for rapid capture of neutrons by atomic nuclei, building up heavy elements through a process called the R process. Based on the observations from GW 170, 817, and subsequent analysis, neutron-star mergers are now believed to be a major, and possibly the dominant, source of heavy elements in the universe. This suggests that the gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, much of this material may have been forged in the depths of neutron stars, squeezed and stretched by tidal forces before being flung out into space. Let us also consider how our understanding of spaghettification has evolved over time, and how modern technology has transformed our ability to study these extreme phenomena. The concept of objects from which light cannot escape predates general relativity by more than a century. In 1783, English clergyman and natural philosopher John Michell calculated that a star with a radius 500 times that of the Sun and the same density would have an escape velocity exceeding the speed of light. Pierre-Simon Laplace independently reached similar conclusions in 1796. These dark stars, as they were called, were based on Newtonian physics and the corpuscular theory of light, which treated light as particles subject to gravitational attraction. When Einstein developed general relativity in 1915, the theoretical framework for understanding black holes changed fundamentally. Light, in Einstein's theory, follows the curvature of space-time rather than being attracted by gravitational force in the Newtonian sense. The consequences for extremely massive compact objects were worked out by Carl Schwarzschild just months after Einstein's publication, while Schwarzschild was serving with the German army on the Eastern Front during World War I. Schwarzschild sent his solutions to Einstein, who presented them to the Prussian Academy of Sciences in January 1916. Tragically, Schwarzschild died of a disease contracted during military service just months later, at the age of 42, never seeing the full implications of his work explored. For decades after Schwarzschild's solution was published, the physical reality of black holes was doubted by many physicists, including Einstein himself. The singularity at the center and the strange properties of the event horizon seemed too exotic to be physically realizable. Some physicists argued that no physical process could compress matter beyond the neutron star stage. This view changed in the 1930s when Subramanian Chandrasekhar calculated the maximum mass for a white dwarf star, the first step in understanding how stellar collapse could proceed. In 1939, J. Robert Oppenheimer and Hartland Snyder published a paper describing the gravitational collapse of a massive star to form what we would now call a black hole. Their work was largely ignored during the war years and the decades that followed, as physics' attention was focused elsewhere. The renaissance of black hole physics began in the 1960s. Roy Kerr's 1963 discovery of the solution for rotating black holes opened new avenues of theoretical exploration. Observational evidence began to accumulate with the discovery of quasars, extremely luminous objects at the centers of distant galaxies that could only be powered by massive black holes consuming enormous quantities of matter. The identification of Cygnus X1 as a likely black hole in the early 1970s provided the first strong candidate for a stellar mass black hole in our own galaxy. During this period, the physics of tidal disruption and spaghettification was worked out in detail. Jack Hills's 1975 paper on tidal disruption of stars by massive black holes laid the theoretical groundwork. Martin Rees and others developed models of how the debris from a disrupted star would behave, predicting the bright flares that would result as material fell into the black hole. The theoretical predictions waited more than a decade for observational confirmation. The Rosati X-ray satellite, launched in 1990, provided the first tentative detections of tidal disruption events in the early 1990s. But these early observations were ambiguous. The signals could potentially be explained by other phenomena. It took improvements in telescope technology and survey strategies to build up a convincing sample of tidal disruption events. The 21st century has been a golden age for black hole observation. The Chandra X-ray Observatory, launched in 1999, has provided exquisitely detailed images of X-ray emission from matter near black holes. The Swift Gamma-ray Burst satellite, launched in 2004, has detected numerous tidal disruption events. Ground-based surveys like the All-Sky Automated Survey for Supernovae, ASASSN, have monitored millions of galaxies for transient events, catching tidal disruptions in their early stages. Perhaps the most dramatic advances have come from gravitational wave astronomy. The LIGO detectors made their first detection of gravitational waves in September 2015, observing the merger of two black holes with masses of approximately 36 and 29 solar masses at a distance of approximately 1.3 billion light-years. The signal, designated GW150914, confirmed a key prediction of general relativity and opened an entirely new window on the universe. Since that first detection, LIGO, joined by the Virgo detector in Italy and Kagra in Japan, has observed dozens of black hole mergers and several neutron star mergers. These observations have revealed black holes in mass ranges that were not expected, challenged theories of stellar evolution, and provided new tests of general relativity in the strong field regime. The Event Horizon Telescope collaboration achieved another milestone in April 2019 with the first direct image of a black hole's event horizon. By linking radio telescopes across the globe into a virtual Earth-sized instrument, they captured an image of the supermassive black hole at the center of the galaxy M87. The image showed a bright ring of emission surrounding a dark central region, the shadow of the event horizon. In May 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. These images do not show spaghettification directly. The material we see in the images is in the accretion disk surrounding the black hole, still outside the event horizon, orbiting rather than falling in, but they represent a triumph of human ingenuity, allowing us to see the boundaries of these extreme objects for the first time. Looking to the future, new facilities promise even more detailed observations. The Vera C. Rubin Observatory, when it begins full operations in Chile, will survey the entire southern sky every few nights, likely detecting hundreds of tidal disruption events per year. The European Southern Observatory's extremely large telescope will provide unprecedented resolution for studying active galactic nuclei and the environments around supermassive black Holes. Space-based gravitational wave detectors like LISA, planned for launch in the 2030s, will observe mergers of supermassive black holes, events far too low in frequency for ground-based detectors. These future observations will refine our understanding of spaghettification and the extreme physics of black holes. They may reveal surprises that challenge our current theories. Physics has a long history of finding that nature is more subtle and more strange than we expected. Let us also consider for a moment the philosophical implications of spaghettification and of black holes more generally. What does it mean that the universe contains objects capable of such complete destruction? In some sense, black holes represent the ultimate democracy of physics. They care nothing for the complexity or value of what falls into them. A hydrogen atom and a human being, a grain of sand and a star, all are reduced to the same fate. Stretched, torn, and absorbed, their information scrambled, beyond any possibility of recovery. The laws of physics make no distinction between precious and mundane, between living and non-living. To a black hole, everything is merely matter and energy, subject to the same tidal forces. This indifference is not malice. Black holes are not cosmic predators stalking their prey. They are simply consequences of the geometry of space-time. Regions where mass energy has curved space so severely that it closes in on itself. They follow the same equations that describe the gentle orbit of the moon around the Earth, just taken to an extreme. The violence of spaghettification is implicit in the same physics that lets us walk on the ground without sinking through it. There is perhaps something humbling in this recognition. Human beings spend much of our lives concerned with our own importance, our own significance, our own survival. We build civilizations, create art, develop philosophies, all in an effort to find or create meaning in our existence. And the universe contains objects that could erase all of that in an instant, that would process our greatest achievements with the same indifference they would apply to a cloud of interstellar dust. And yet there is also something remarkable about our position. We are arrangements of matter complex enough to understand the very forces that could destroy us. The same physics that predicts spaghettification also gave us the ability to build radio telescopes, to detect gravitational waves, to image event horizons. We are made of atoms forged in stars, and we have learned to comprehend the depths of stars and what lies beyond them. In all the known universe, black holes are among the most extreme and fascinating objects. They challenge our intuitions, push our theories to their limits, and remind us how strange and vast the cosmos truly is. Spaghettification, the process by which they destroy anything that ventures too close, is a window into this strangeness. By understanding it, we understand something profound about the nature of gravity, space, time, and matter. As we conclude this journey, remember that space exploration has always been about pushing boundaries, both physical and intellectual. The early astronomers who first turned telescopes to the sky could never have imagined that their descendants would detect ripples in space-time from colliding black holes billions of light years away. We cannot know what future generations will discover about these most extreme of cosmic objects. What we can know is that the universe is vast, strange, and beautiful, that it contains wonders beyond our current imagination, and that the human drive to understand will continue to push the boundaries of the known. Spaghettification may be terrifying, but the fact that we can understand and describe it is a testament to the power of human curiosity and the remarkable reach of our science. Thank you once again for joining me on this exploration of one of the universe's most extreme phenomena. The cosmos is full of mysteries waiting to be unraveled, and together we will continue to explore them. If you've enjoyed this journey to the edge of physics, please consider supporting the channel so we can continue bringing these stories of the universe to you. Rest well tonight and dream perhaps of the strange and wondrous cosmos that surrounds us. The universe may be indifferent to our existence, but that indifference makes our existence no less remarkable. We are the cosmos becoming aware of itself, and there is profound beauty in that. Until we meet again among the stars,